The International Space Station isn't just a laboratory for experiments about how the human body responds in being in weightlessness. It's a place where scientists are studying how many things behave when there is no gravity present. In one experiment, researchers are examining the behavior of liquids inside containers. It's called the SPHERES Slosh experiment, and flight engineers Kimia Yui and Chell Lindgren will be conducting another experiment run later this week. This morning, we're going to learn more about that experiment from Jacob Roth, the co-principal investigator who joins us from his office at the Kennedy Space Center in Florida. Good morning, Jacob.
Good morning, Amiko.
Thank you for joining us here. SPHERES Slosh. So, can you tell me, start by just explaining in the SPHERES Slosh, what are we looking at, or the behavior of all fluids, or are we looking at only some in particular?
So here at the Launch Services Program, we're particularly concerned with launch vehicle upper stage propellants and how they behave during coasts or before separation events. But the experiment was really designed as more of a broad study of general fluid behavior.
Briefly explain, why are we wanting to understand this?
So particularly for upper stage propellants, we get concerned about what the fluids are doing. You fire your engines and you're under a gravity environment, and then you go into a coast and the fluids move around. And predicting where they are, what kind of walls will get wetted, what kind of moments that might generate on the rocket itself, what that might do to your separation attitude for a spacecraft. All of those things are very difficult to predict and can have a big effect on the mission success.
Okay, so talk to me about the SPHERES satellites. How are those being used to contribute to this research?
So the SPHERES really had two advantages. The first advantage was that they have a kind of a reproducible, consistent thrust. Turns out that thrust is a little low, so we can only use it in certain situations. But that was kind of the big thing. But the biggest reason we used them more than anything else was that they were already on station. So we took advantage of their power. They had a lot of capabilities, the computers, and all this stuff was already there. Saved us from having to build it ourselves and made it a lot quicker and a lot easier to get on the station.
Describe what happens during one of those experiment sessions.
Yeah, so after setup, after they get everything buttoned up and everything put together, we have a series of test maneuvers. We found out in our first checkout session that there's a lot of bubbles that form inside the liquid, and that makes it really hard for us to get a good initial condition. So before every maneuver, they perform what we call a settling maneuver, where they spin it either around one sphere or around the center to try and get the bubbles out, and then they slowly slow it down so that they've got a good initial condition. After that, we'll perform a maneuver where we start data collection, and then a given maneuver will happen. Either the spheres will fire and move it around a certain trajectory to try and see what the fluid's going to do, or we'll have the astronaut push it or pull it or rotate it or push it and let it float across the room. And during that whole time, we're taking accelerometer and gyro data as well as images to get an idea of what the fluid's doing. And we'll perform a series of those maneuvers until we run out of time, and we'll tear everything down and download the data.
Okay, so, with all the sophisticated computer programs to model all sorts of phenomena, why would we need to use this type of demonstration? What makes this practical?
So that's a very good question, and it's really the point of this practical demonstration, this type of experiment, was to improve those models. Computer programs and models have been written. We have the computational fluid dynamics as well as pendulum slosh models, but they've all been validated in 1G cases. They've all been validated against, experiments that have occurred on the ground. And so we really don't know how well they predict low G environments. So this experiment was really designed to make those computer models better, or to make us have less uncertainty about how well they're predicting.
Now, your experiment arrived on the station about 2 years ago. I can't believe it's already been 2 years. So how many more sessions are you planning, and what can you say about what we've learned so far as a result of the sessions we've had?
Okay, so we have this session this week. We have one additional session left after that. In addition, we're also planning, possibly in the next year, to send up a pair of at least one, if not two, tanks. We're hoping to do a little bit more now that we've studied how they behave. We're going to be putting some internals inside the tanks and trying to understand a little bit about how we can contain or control the fluid so it stays where we want. As for what we've learned, we've really learned a great deal about how unintuitive low-G fluid behavior is. We do know from some initial looks that our models have proven to be fairly accurate at bulk fluid motion, but we've also found some good areas for improvement. Particularly, we struggle with bubbles and droplet behavior and whether or not they recollect into the bulk fluid or not. That's been very difficult for us to predict. I will mention that some of this data we've already used to improve our models and to reduce our uncertainty, particularly for the MMS, the Magnetospheric Multiscale mission that launched in March. They were very concerned about fluid behavior during their multi-spacecraft separation sequence because they had 4 spacecraft that had to be separated in a particular interval with particular attitudes, and they were very concerned about what the fluid would do. And so this data was helpful in easing their worry a little bit.
Well, this is certainly interesting and really great that you guys are able to make use of the SPHERES satellites that are already in place on board the International Space Station. Also, I understand that there's an education outreach component. Can you share with me some of your results with the middle and high school students that you guys have worked with?
Yeah, so we've worked with a wide range of students. Starting at the college level, we've had Florida Tech built this apparatus, and we continue to work with them as we do all of the individual sessions.
Houston on 2, no
for the younger
required,
students, given how visual our results are, how great the pictures and videos are, we use that really well to get them engaged. They particularly find the fluid images and videos fascinating. We've also particularly engaged with FIRST Robotics. It's a robotics competition. And we've given a number of presentations to them on how using that type of robotics can be done for real science. And then we've also been working here at the Kennedy Space Center Visitor Center to provide presentations to visiting student groups.
Great. Well, thank you, Jacob. I think that's all the time we have. Thank you so much for joining us and answering some of these questions. Good luck to you and your team as you continue to research this. And best of luck to you guys.
All right. Thank you.